I want to talk about NSA surveillance. That's been in the news lately. But most people don't know how they do it, how they actually do it. How can they read our emails? How can they sort of eavesdrop? Well, it turns out it's based on very sophisticated math and some super long and super big numbers. And I'm going to show you some of those numbers. Does it sound good?
Yeah, we love numbers.
Well, I have to set it up a little bit. I want to talk a little bit about something, which we use in our everyday life, the clock. So let's say you start working at 9 in the morning, okay? And you work for 5 hours. When do you finish?
You finish at 2.
Okay, but if you were to calculate 9 plus 5, you get 14. Why do we say 2 p.m. and not 14? That's because 14 is 12 plus 2. So when we get a result, like 14, which is larger than 12, then we sort of just take the remainder. This is called clock arithmetic. And also in mathematics, we call it modular arithmetic, because we say that 9 plus 5 is 2 modulo 12. Modulo just means that we retain the remainder. So likewise, we can imagine a clock which doesn't have 12 hours, but has any other whole number as the number of hours. For example, it could be 10 hours, could be 5 hours, could be 5,368 hours. But actually in mathematics, the best clocks are the ones in which the number of hours is a prime number. It turns out that actually there are some really sophisticated things about this arithmetic. But of course, this sophistication one can only feel when that number of hours becomes larger. If it's all modulo 7 or modulo 12, there isn't so much room to create something complicated that we could use in encryption, say. But if that number is zillions of zillions of zillions, then that opens the opportunity to do something that other people cannot crack. For example, when we send our credit card number online, or we send an email, it gets scrambled and then gets unscrambled at the endpoint. That is based on this kind of arithmetic with some very large prime number of hours. And I'll show you what the actual numbers involved in a bit. But let me explain a little bit more about what these algorithms are based on. So first of all, they're based on this clock arithmetic, as we already understand that. And there is one more layer, which is that we also look at equations, at an equation with two variables. The kind of equations that go into the algorithms that NSA was able to crack have to do with what mathematicians call elliptic curves. So an elliptic curve is something which is defined by an equation like this. Y squared equals x cubed minus 3x plus 5. So that's an equation on two variables, x and y. To solve this equation means to find two numbers, x and y, such that the left-hand side is equal to the right-hand side. But there is a crucial element. Where exactly do we look for solutions? There are many options. Of course, the obvious choice would be to look for solutions, say, in real numbers. And then this will actually give us a curve which will look something like this. Every point here will have two coordinates, x and y, and if you plug them into this equation, left-hand side will be equal to the right-hand side. So that's the most obvious way to think of solutions. Being armed with this new arithmetic, the clock arithmetic, we can also look for solutions modulo some prime number, right? Nothing can stop us from doing that. So for example, we can choose x and y to be elements of this set of possible hours on this 7-hour clock, and we can try to look for pairs x and y such that the left-hand side is equal to the right-hand side. So this way we get something like, think of this as sort of like maybe some points on this kind of curve.
So there are less solutions?
There are fewer solutions for sure, because, well, to begin with, x and y can only take values from 1 to 7. And we can sort of think of them as some special points on this curve. And of course, if you take a very large prime number, then there will be many more solutions than if you take a small one like 7. And there is a whole industry in mathematics which is called elliptic curve cryptography. And elliptic curve cryptography has to do with using these solutions to scramble and unscramble messages when they're transmitted. There are some standards in this area which were set by National Institute of Standard Technology, which is a body in the United States which is responsible for this kind of things. They came up with these standards, and in fact you can read. This is all public knowledge. This was not classified. Here is the algorithm, which is called this dual elliptic curve deterministic random bits generator. So you see the elliptic curve is prominently featured here, and this is the equation. This is exactly the equation that I wrote.
It's a very simple equation.
It's a very simple equation, but you have to pick a prime number. In this document, they actually give you details. They provide you this number p, So see, this is the first large number. Gives you the largest clock that you've ever seen. Look how many digits there are.
So that's the clock they're using on their curve.
That's right. So on their curve, on their equation, they're using this many hours. Okay, so in their day has many more hours than we're used to, in some sense, right? And then there's some additional data that have to be used in this algorithm, and so you use those data, and as a result, you create something which produces numbers that look totally random. Those numbers themselves do not live on the curve, but the curve is used to produce them. It's actually a very important problem in mathematics to produce numbers that look completely random. So this by itself is not an encryption algorithm. It's not used to encrypt a specific email or a specific credit card number, but rather it produces something based on which other algorithms, which would actually be encrypting your emails or your credit card numbers, be working. It will be based on that. That's a flowchart which generates random numbers. You start with something, and then there's sort of like a loop which creates more and more and more numbers, and then they get scrambled, and then the output is some number from which you just extract bits. And the way it's set up, it should be so that they are completely random. That, in other words, if somebody reads those numbers, they cannot predict what's the next number coming out. So in addition to this equation itself, in addition to the prime number which is given, what makes this work is a pair of solutions.
You need this to kickstart things, do you?
That's right, to kickstart and then to keep going. P is used to run the cycle, to produce the next one and next one and next one, and Q is used to kind of scramble the output of that cycle, so that in theory nobody would be able to predict what's the next one. Think of the solutions as being some points on a curve. And this, by the way, is very difficult to find those solutions because the numbers involved are huge. So it's not an easy task at all. But the government agency is sort of simplifying our life, and they're saying, look, you don't have to look for solutions yourself, we'll give you the solutions, we'll give you these 2 points, okay? So here's P, maybe he's here, and Q is here. And they just give you this. So these are the numbers, actually, you can see them here.
Oh, this is our big money shot.
This is our big money shot, PX, PY, QX, QY. These are the numbers which the government says, these are the solutions, and actually anybody can. This is public information, it's public knowledge. Anybody can take these numbers and substitute in the equation and see that indeed the equation is satisfied. But they found this for you. Okay, so now they suggest to use these 2 numbers to run this random number generator.
If all of these companies used the same equation and the same numbers provided by the government and then started their flowchart machine, weren't they all generating the exact same numbers?
Good point. There is a seed also. You have to start with something, and that you can choose yourself. And of course, that's what will distinguish your sequence from other people's sequence. But they give you P and Q, which are kind of like the 2 steps which provide the information to run the steps of the procedure. Right? It's a multi-step procedure. It's a flow chart, really. And to implement those steps, you need those 2 points. And what is implicit here is the suggestion that these 2 are kind of random. P and Q are kind of random, that they don't bear any relation with each other. So it's almost like they give you 2 random villages in Australia, and they say, and you're like, you've never been to Australia, so you don't know, where they are, what the distance between them is, and you expect that no one else would know. It may not be such a good analogy because, of course, in case of villages in Australia, you can easily find out what the distance is. But imagine something where actually it would be incredibly hard to find the relation between 2 numbers. But imagine that somebody actually knows what the relation is. And as now we find out, actually NSA apparently did know a relation. And then the point is that in that case, there is a backdoor. That you can use that information, sort of the distance between the 2 villages in Australia, you can use it to be able to predict the outcome of the algorithm. Once you know, you can observe it for some period of time and see what numbers are coming out, then you can actually find out what the next ones are going to be. And that sort of throws a whole sort of a monkey wrench in the whole procedure, because then it gives you a way to peek into this other encryption algorithms which rely on this random number generator. And that's what happened.
What has the NSA got, or what did they do that meant they were able to find the relation, but spies from other countries or mathematicians like you can't do it? Or did they reverse engineer it? Did they make the equation?
They reverse engineer it, yes, that's the point. And the thing is, it's very hard to find that relation if you don't already know it. And this is actually the basis of this whole idea of encryption based on clock arithmetic. That there are certain problems when you do in clock arithmetic which are intractable. It would take years, even on a network of supercomputers, to be able to find a solution.
So in the video description there's going to be a bunch of links you should have a look at. That's going to include documents that we discussed in this video. They're all public documents. A continuation of the discussion I had with the professor that didn't make it into this video, and that covers a whole range of interesting topics like the people who actually foresaw that maybe this was a problem, why companies were spoon-fed this information, and also the importance of mathematics in the world these days. It's worth a look. And I'll also include a link to Professor Frenkel's book. This is it here. It's called Love and Math. It's really good. It's worth a look if you're into mathematics books. And you should be, because you're watching Numberphile. And lastly, thank you to everyone for your support through 2013 and watching Numberphile. It's been great fun making videos like this, and hopefully there's going to be a lot more in 2014. Cheers.